used in sports? Thank you. So can you tell me, do anybody of you playing sports? आप लोग sports खेलते हैं? I think this is a very important part of our life. Either we play sports or we watch sports, but I think this is a very crucial part of our lives, of an activity which most of the people do either by doing the sports or either by watching the sports. So tell me about your sports activities, and any, have you ever thought that mathematics is used in the sports as well? Anybody? Yes, Rahil, do you want to say something? Isha is saying that you played volleyball. Okay, Isha, uh, I think Isha is here. Okay, Isha Shahzad, so can you tell us how, have you ever thought that some mathematics is also involved in sports, or in the sports you are playing?
Maybe sometimes you have to calculate the direction in which you throw the ball.
Yes,
You have
very.
to estimate how far it can go.
Yes, in real life, when you're playing the volleyball, so I think at the moment when you are playing, you cannot measure the or you cannot estimate the direction, but uh, afterwards, or whenever you're analyzing your game, you can have some directions, maybe some optimized directions which can score.
Sir,
Yes.
I was thinking, can graph theory be used to figure out the number of matches that can be held between a particular number of teams so that no two teams are playing against each other twice?
This is the topic of our today's session, that I'll tell you the scheduling problems, and we will tackle using the graph theory. So I hope you will get the answer of this question at the end of this session. By the way, good question. Anybody else? If you have, like, if you ask some some questions related to sports and mathematics, you can pose those questions. We can think about those questions, the answers of those questions in the session as well, or afterward.
Uh, Teamwork is often important in sports. So you may have a scenario where player A likes playing sports with player B, and B likes playing with C, and you might draw a kind of directed graph to show the arrows of likeness from. So if you draw an arrow from A to B, that means A likes playing sports with B. So you might have to figure out a way to make a team that everyone's happy with.
Yes, you're right. Uh, Anybody else related to sports and mathematics? You have thought about sports and mathematics? Coaches
Um,
most of the time use mathematics. Okay, somebody is saying something.
yeah, it's just me. I was just wondering, if you represent players on a football field as vertices and the passes between them as edges, and
Yes,
I don't know, that would be a.
yes, you're right.
I don't know how much useful information you could get out of it, but
This is
marking how many passes were between two players or if somebody else
very useful information, and the coaches takes this information. They have analyzed. They have people who are analyzing these things, and they take those graphs which tell all these things, that the the and this time the graph will not be a static graph. The graph can be the dynamic graph, in which the vertices can
Yeah.
and change their positions as well, and the edges between them also changes between them. So a lot of things happening. A lot of mathematics is happening there. Uh,
But usually when we think of, I don't know, haven't done much graph theory, but usually when we think of those vertices, they don't really move, like their position, the way you draw it doesn't matter. But I don't know, if
yeah.
you're visualizing it in a domain, then positions also get important, right? It's a dynamical system that's going on.
So yes, these are two branches of graph theory. The most which we have used as an undergrad courses, these are static graph theory. So in which the vertices are static, they are not moving. We are not discussing when, if with the passage of time, they are changing their. It is not important their position. The thing which is important, that with passage of time, they are changing their connections with other vertices. So the edge gives you the connection between the two players or the two vertices, and with the passage of time, it changes. As you mentioned in the, if you model this the football game and model each player as a vertex, and you model that the passes as the connection between the as an edge between the two players or two vertices. So since with the passage of time, the passes changes. So this is not a static graph, this is dynamic graph. uh, so everywhere in which the connections are changing with the passage of time, we can deal with the dynamic graphs, not with the static graphs. So, but today's topic is related to static graphs. So the overview of today's talk is, first I will give you some types of tournaments, and then we study some terminologies in graph theory, and in the end we will see how the graph theory relates the scheduling of the tournaments. So let's see first the different types of tournaments. So as I want that this session should be interactive, so whenever you have any question, any remark, please raise your hand or just start talking. Okay. So mainly there are three type of tournaments, in which the very important tournament is the round robin tournament, in which each team plays exactly k games against each other. Usually we see the tournaments in which the team in the league games, especially in the league tournaments, we see that each team plays exactly two games against each other, one home and one away. But there are tournaments like, if you saw the World Cup 2019 Cricket World Cup, it was played round robin, that every team plays exactly single game against each other. My main today's talk is about this single round robin tournament. Second is elimination tournament, in which the tournament progresses n rounds, and in each round some players are eliminated and surviving players are paired in future rounds, where again losers are eliminated. So people who lose, they eliminate, and the people or the teams they won, they progresses to the next rounds. This is called the elimination tournament. I think you saw such type of tournaments in tennis. If I'm not wrong, Gautam is playing tennis, so he may correct me. So usually tennis tournaments are elimination tournaments. Uh, One also king of the hill. In this tournament, a player or the team stays in the court as long as he or she can bear the next challenger. Most of the time, when we are in the in the courts like badminton court or tennis court, so we will do such type of things, that a player who wins he stays, and the people who loses, they leave the court, and the player um, will stay as long as he win the matches. So these are some types of tournaments. My topic or my session, today's session will mostly go around the round robin tournament, and I'm more focused on the scheduling of the single, which is a very simple single round robin tournament. So before going to start the scheduling of the tournament, let's see first the what is graph and what are the different related concepts in graphs which help us in scheduling the tournaments. So graph, you can say a graph is a finite set of dots called vertices and connected by lines called edges. So which can be directed. जैसे आपके पास ये एक सामने फिगर बनी हुई है. Last time I give you very abstract definition. This is an abstract definition that you can say that graph is just a finite set of dots or points. We call these points as vertices, and we have another set. Okay, so this set we call V, the set of vertices, and we have another set E, as we say that they are connected by lines, which is we call edges. So we have another set E in which we have pairs of, so actually E is a subset of this set V2. V2 is V times V, the Cartesian product of E with V. So E is actually a subset of V2. For example, let's suppose I have a set V. The elements of these are 0, 1, 2, 3. So 0, 1, 2, 3, or here one is missing. So 0, 2, 3, 4. And the set of edges is consist of the pairs like 0, 3, 0, 2. Use 0, 3, 0, 2, 2, 4, 3, 4, 0, 4. And what was missing? 0, 3, 0, 4, 0, 2, 2, 4, 2, 3. So E is a, you know that here E is a, okay, here not E is a subset of V cross V. V cross V, the element of V cross V's are in the form of ordered pairs. Vi comma Vj, where Vi, Vj belongs to V. But here E is a subset of power set of V. Okay, so since Rhyme also mentions the directed graph. Here, this example is an undirected graph. So when we have an undirected graph, so the abstract definition is that you have a set V and a set E, which is a subset of power set of V, and it contains, E contains 2 point sets, 2 points subsets of V. Okay, so here all the subsets are 2 points. So such a graph is called indirected graph, and this is actually the geometric realization of that graph. Mean you take the points of the vertices or the point of the main set V. So graph is V and E. The pair you can denote it by G. And the geometric realization of this graph that you just point, you take a dot of each point in the set, and for each set like 0, 3, so you will connect the dot of 0 with the dot of which you denote by 3. So like this line segment, and then 0, 2, and all these lines. So the elements of E will be described by edges. So in this way, you will get an undirected graph. Okay, so now if I take E like this, for example, with as a subset of V cross V. So for example, I take 0, 3, 0, 2, 2, 4, 3, 4, 0, 4, and 2, 3. So now I take the ordered pairs. You know that in ordered pair, 0, 3 is different from 3, 0. Okay. So that's why I take ordered pair. So when I take like this, so this graph is again a pair of two things, but here the E set is a subset of V cross V, and this is called the directed graph. This is called undirected graph. This is called directed graph. And what is the geometric realization of the directed graph is that we make an arrow, not in a line segment, but an ray. So the ray started from 0 to 3. So now we make an arrow from 0 to 3, 0 to 2. So we make an arrow from 0 to 2, 2, 4. So we make an arrow from 2 to 4, 3, 4. We make an arrow from 3 to 4, 0, 4. We make an arrow from 0 to 4, 2, 3. We make an arrow from 2 to 3. So this time the edges are directed line segments or rays, in which the arrow's direction will be the incident point is the first point of the ordered pair. The final point of the ray is the, the second point of the ordered pair. So I hope you understand the two types of graphs. The abstract definition for the undirected graph is that it is a set with another. It is a pair of a set consisting of points and another set E, which is some subset of a power set which contains only subsets containing 2 points. And for the directed graphs, again, V is the same as a finite set, but E is this time is a subset of V cross V. So this is called the directed graph. I hope everybody understands this thing. Okay. We can also use the arcs. It is not necessary that we can use the line segments. We can use arcs for the and also, for example, if there is a graph in which we have like I put two last time we have seen such graphs which I put for the Königsberg. So if you remember, last time I do this thing. The graph of Königsberg bridge problem was like this. There are multiple edges between the two vertices as well. So such type of graphs are called multigraphs. Mean you can attach more than one edge between two sets. Okay. So such graphs are called multigraphs. So there are some terminologies related to graph theory. First is when you say that two edges are adjacent. We say that two edges are adjacent if they are connected by a common vertex. If they are connected by, for example, the edge small a and small b, they are adjacent since they are connected by the they are connected by a common vertex. Similarly, you can define about the two vertices. The two vertices are adjacent if they are connected by an edge. Okay, so you can define the adjacency between the vertices and is about the degree. So in directed graph, we have two terminologies for degree: the in degree and the out degree. So the in degree represents the number of edges entering the vertex, like you have here this graph. So we the in degree of a vertex. So we are defining the degree for the vertex. So for example, if we have 2, so we have to see that how many edges will entering this vertex. So since you see this edge is entering into 2, this vertex is entering into 2, so we can say that the in degree of the vertex 2 is 2. Similarly, the out degree denotes the number of edges going out of the vertex, and so out degree is of 2 is 1, because there is only one edge which is going out from 2, and the degree is the sum of in degree and out degree. So like in 2, you have 2 in degrees and 1 out degree, so the total number of the in degrees and out degrees is 3. So 3 is a degree of this vertex 2. Okay, so that's how you define the degree of a vertex. Understand? This tells you, this degree information tells you, for example, if you have only this table, you do not have any graph, but you have this table, you can make the graph very easily. Okay, because it tells you that how vertices are connected with edges. Clear? So degree is very important information about the graph. It tells you about the whole structure of the graph. Next is the definition of a complete graph. So a complete graph is a graph in which each pair of graph vertices is connected by an edge. So हर pair जो है वो connected हो by an edge, then you can say that this is a complete graph. So in terms of set theory, so the set E will be consist of all subsets of V containing 2 points. Okay, so a complete graph has a set E which consists of all subsets of V which contains 2 points. So in general, we can take any number of subsets of V which contains 2 points, but when we take all subsets of V containing 2 points, we can say such a graph is a complete graph. So here are some examples. We denote the complete graph with n vertices by capital K subscript n. So here are some examples like K2. 2 means the number of vertices. So we have 2 vertices. So there is only one edge because there is only one set containing these 2 points. K3 is this triangle. Every pair of vertex is connected by an edge. You have K4, K5, K6, and so on. Question. The number of edges in the complete graph of n vertices. So who tell me the number of edges in the complete graph of the n vertices? Okay, Saad says NC2, C means combination and or choose and choose 2 and combination 2. Okay, Saad, what is the reason for saying and choose 2?
So basically we have to pair 2 vertices for an edge. And since we aren't considering ordered pairs, then we don't need to consider permutations, and hence we have NC2. So we have combinations.
So do you know what is NC2? How you define NC2?
Yes. N factorial over n minus 2 whole factorial multiplied by 2 factorial. And from n terms, you choose 2 terms that pair each of the 2 elements of n. It's a way of choosing elements of n.
Yeah, you're right. So n choose 2, yes, it's right. N choose 2 because you have n elements, and whenever you have an edge between any pair, so in other words, you are pairing these 2. because we are saying that you have to all subsets containing 2 points. So you are pairing these two, and we do not have the order is not important here. So that's why we will take NC2. Good. And when we solve NC2, it will get n into n minus 1 divided by 2. So let's suppose, for example, if you have n is equals to 2, so you have one vertex. When we have n is equal to 3, so 3 into 2 divided by 2, we have 3 vertices. When we have n is equals to 4, so 4 into 3, 12 divided by 2, 6. So we have 1, 2, 3, 4, 5, 6. Sorry, it's 5, 6. So, so the number of edges in a complete graph is given by this formula. Okay, this is very important. Complete graphs will help us to uh, to to schedule a Robin round tournament of single elements. Next is the concept of edge coloring, which is a very important concept. An edge coloring of a graph is an assignment of colors to its edges so that no two adjacent edges have the same color. Like you have seen in the graph, this is the edge coloring graph of a graph, that no two uh, adjacent edges. So adjacent edges means that they have common vertex. So if two edges have common vertex, then they must assign different colors. So if this is a situation, this is called the edge coloring of a graph. And there is one more terminology related to coloring. This is the chromatic number. The chromatic number of a graph is the least number of colors it takes to color its edges so that adjacent edges have different colors. So how many you need such colors? The number of such colors, the least number of such colors uh, for a graph to be edge coloring, to do the edge coloring, is called the chromatic number. Okay, correct, right? Do you understand this thing? Very easy.
Yes, sir.
Next is bipartite. So there are, as you seen the complete graph, we have complete bipartite graph, but before this, what is bipartite? So bipartite is that if we partition the vertices into two disjoint subsets, such that no two graph vertices within the same set are adjacent. Mean you divide your set of vertices into two disjoint sets, U, V, and now you take the subsets. You take an element first, take an element from U, and the second element you will take from V. So if you do like this, so you are pairing the elements of the whole set. Let's suppose the whole set is W, and W is a union of V, U, and V, and U and V are disjoint. By the way, this is the symbol for disjoint union. So such a graph is called bipartite graph. So this is an example, this graph. So here we have 1, 2, 3, 4 vertices on the left are from U, and 1, 2, 3, 4, 5 vertices on the right from the set V, and you connect the with the vertices of U with the vertices of V, and you do not connect the vertices of U, and you do not connect the vertices of V. Okay, so such a graph is called bipartite graph. In other words, you partition the graph into two set of vertices. And in the complete bipartite graph, if every vertex in U is connected to every vertex, so you will do the all type of pairing which you can do between the edges of U and V, then you call such a graph as the complete bipartite graph. Okay, and you would denote it by K, R, comma, S. Here R tell you R is the number of vertices in U, and S is the number of vertices in V. Okay, so these are the That's how you denote the complete bipartite graph. Clear this bipartite thing and the complete bipartite graph thing. Next concept is tripartite graph. So a complete, or you can say not complete. Okay, yes, a complete tripartite graph is one where we can divide the vertex into three sets, V1, V2, V3, such that no two graph vertices within the same set are adjacent. Within the same set are adjacent means that the vertices of the same set do not connect by an edge. Okay, this time you are taking three sets, like if you see like graph in the example, you have three type 1, 2, then you have 3, 4, 5, and then you have 6, 7, 8. So there are three type of vertices, and you connect the vertex 1 with each vertex of, let's we call it, this call it V1, we call it V2, and we call it V3. So one V1's one vertex is connected with 6, 7, 8. Also, it is connected with 3, 4, 5. Similarly, 2 connected with 6, 7, 8, 1, 2, 3, 4, 5, but it does not connect with 1. So such a graph is called complete tripartite graph, and we denote it by this letter K R S T, where R represents the number of vertices in V1, S represents the number of vertices in V2, and T represents the number of vertices in V3. Okay, good. Next is a very important concept of matching. So if a collection of edges are disjoint from each other, it is called matching. If you take a collection of edges which are disjoint from each other, disjoint means that like this, for example, if you have this, so this is called the matching. So you have a collection of two edges which are disjoint from each other. So we call such a collection of edges as matching. So if a graph G has a matching M, which includes all of the vertices of graph, then M is a perfect matching. So you take, you call a matching as the perfect matching if it includes all the the vertices of the graph. Okay, so if you take all the vertices of the graph and you take a matching, then you call it the perfect matching. If you take a matching, means that you collect all the disjoint edges of a graph. Okay, now how do you get the perfect matching? What is the condition? The condition for perfect matching is that the number of vertices of graph must be even. Okay? So whenever you have a perfect matching, then the number of vertices of that graph must be even. So if you have an even, so if you have an odd number of vertices in a graph, then that graph does not have a perfect matching. You can also call the perfect matching as a one factor. But what does it means by one factor? So I define a general definition, a K factor. A K factor is a subgraph of a graph which includes all the vertices of graphs and where each vertex in the subgraph has degree K. So you understand, the K factor is a graph, subgraph of a graph, which includes all the vertices of the graphs where each vertex in the subgraphs has degree K. First thing is that it includes all the vertices, and second thing is that each vertex is each vertex in the subgraph has degree K. Okay, I gave you some examples of these things, and the one factor is the perfect matching. So one factor means it is a subgraph of a graph which includes all the vertices, and each vertex in the graph has degree 1. So degree 1 means that it connects only the number of edges attached with that vertices is 1. Okay, for example, I take this graph. By the way, this is the complete graph. This is K4. So I can find a perfect match. So let's suppose if I take this vertex, and this vertex. Okay, so this is a subgraph, and it is a perfect matching. It is a one factor as well, because each vertex. So first thing, that it includes all the vertices of the graph. Yes, it includes all the vertices of the graph. And the second thing is that each vertex in the graph has degree 1. So this in the subgraph, you have to see in that subgraph. So I call them 1, 2, 3, 4. Then 1 has degree 1, 2 has degree 1, 3 has degree 1, 4 has degree 1. So do you understand? Now the red is the subgraph, which I can call as one factor. Can you tell me any other one factor? So I write in the form of the set. So this is the subgraph I'm taking from here, which is a one factor. Can you tell me any other one factor? Anybody of you?
1, 3, 2, 4.
Yes, good. 1, 3, 2, 4 is another one factor. 1, 3, 2, 4. Can
1,
anybody?
4, 2, 3.
1, 4, 2, 3. Very good. 1, 4, 2, 3. These are all, you can say, perfect matching or one factors. Can anybody tell me two factor in this, from this graph?
One,
1, 3, 3, 4, 4, 2, 2, 1.
Sorry, please repeat. 1,
1,
1,
3,
1, 3,
3, 4,
3, 4,
4, 2,
4, 2,
2, 1.
2, 1.
Yeah, that was it.
That's it.
Yes.
1, 3. This one is
I
1,
think.
3, 4, 4, 2, 2, 1. Good. So every vertex has two edges. So blue is the subgraph of the original graph, and all vertices are there in this graph, and the degree of 1 is 2, degree of 3 is 2, degree of 4 is 2, and the degree of 2 is 2. So yes, this is a two factor. This graph. Good, very good. So these matching things are also used in the in scheduling. So that's why I mentioned this concept here. So up till now, if you have any question, please tell me about the graph, about any concepts related to graph. We have seen the adjacent vertices. We have seen adjacent edges. We have seen the definition of complete graph. We have seen the definition of bipartite graph. We have seen the definition of complete bipartite, tripartite graph, and complete tripartite graph. And in the last, we have seen the definition of matching, perfect matching. And the condition for perfect matching is that the number of vertices of a graph must be even. So if it is a perfect matching, then the number of vertices in the graph is even. But there are examples in which the number of vertices in the graph is even, but you cannot get a perfect matching. Okay. And what is perfect matching? Perfect matching, you can say it is a one factor. It is a one factor means that what is the definition of a one factor? That it includes all the vertices, and the degree of each vertex is 1 in the subgraph. Okay, so if you have any comment, any question, otherwise I'm moving forward towards the sports scheduling thing. So first, uh, we were going to see the round robin tournament. I repeat that the round robin tournament, given a collection of teams, play a competition such that every two teams play each other a fixed number of times. Okay, most of the tournaments are round robin tournaments, or the tournaments in which they divide all the teams in groups, and then each group, the teams in each group will play with other uh, teams a fixed number of times, and usually it is one number of times, but it can be happen that they will play with many matches, but they play a fixed number of times. And for such tournaments, the complete graphs describe the whole tournament. Okay, so I'll show you with different examples that if you have four teams, five teams, then what will happen. So let's start with if you have, for example, four teams. So this is the graph which represents the tournament in which four teams are participating and they are playing with each other one time. So I represents the team with the numbers 0, 1, 2, and 3. So these are the names, you can say these are the names of the teams, and I take a point for each team, a point or a dot. Okay. And then since 0 have to play it with each 1, 2, and 3, so I take an edge from 0 to 3, 0 to 2, 0 to 1. Similarly, 2 has to play it with each, so I will take the edges from 2 to 0, 2 to 1, 2 to 3, and so on. So first tell me how many matches will be played. Number of matches will be the number of edges of this graph. 1, 2, 3, 4, 5, 6, which is the number which the number of the complete bipartite edges. Okay, which you remember this is you have four teams, so 4 into 4 minus 1, which is 3 divided by 2. Okay. Okay, I also use different colors here. I use three type of colors: blue, red, and green. So in a round robin tournament, you know that there are rounds. So there are matchings here. If you take a matching, let's suppose 0, 3 and 1, 2. So one matching 0, 3, 1, 2. This matching 0, 3, 1, 2. This is one matching, and this matching shows the one round of the uh, of the tournament. Okay. So how many rounds are there for the tournament of four teams? They are playing round robins. So number of rounds is equals to 3, because there are six teams, and each team is sorry, there are four teams, not six. There are six matches. So there are four teams, and you have to pair. So all at any stage you will pair. You get two pairs of the teams which are playing against each other. So let's suppose in week one, uh, one is playing with two. So this is a table which I take. Um, okay, first thing is that it can be played in 6 weeks. Like in every week there is one match. Okay. The thing is the every team has to play it once in 1 week. Okay. So it can be done that the tournament goes to 6 weeks, and every pair or every team played once in a week. But the tournament will finish earlier. It can be finished earlier if we can finish it in week 3, and we can do this in 3 weeks uh, by taking the matchings, the perfect matchings. Okay. So let's suppose in week 1, if 1 is playing with 2 and 3 is playing with 0, these are the matches which we played in the week 1. In week 2, 0 is playing with 2 and 3 is playing with 1. The red lines are showing the red one is showing the, so red one is showing week 2, blue is showing the week 1, and the black is showing the week 3. So in 3 weeks, the all the players will play all the matches. Okay. Okay. Let's see what about in 5 teams. If we have 5 teams, now we need more colors. We need more weeks. Why we need more weeks? Because we have number of matches are more than the previous. So how many number of matches this time? Now we have 5 teams, 0, 1, 2, 3, 4. So number of matches will be 5 into 5 minus 1 divided by 2, which is
10.
10.
10.
So there will be 10 matches. Okay. And we have 5 number of teams. Now, can you make, as we have studied that there is no perfect matching when there are number of vertices as odds. So whenever we try to make a perfect match, you cannot make a perfect match, but you can make a match. Like for example, if you take 0, 4, the blue ones, and 1, 3. This is a one match. This is a matching, but this is not a perfect matching. 0, 4, and 1, 3. Okay, this is a match. Okay, Zainab is asking to repeat the 4 teams part again. Okay, I can repeat uh, after this. Okay, so carefully listen to the 5 teams and then I'll go again for the 4 teams. So, so we have a matching 0, 4, 1, 3. So one edge is missing in this time, which is 2. Okay, so we can do this thing that we will give this team as a buy. Buy means that they will not, that team will not play that week. So this means that in every week, if we are doing a matching, then one of the team must have to be get a buy. So in the first week, let's suppose 0 is playing with 4, 1 is playing with 3. So I take the blue color for the first week. Okay, and 2 is resting on that week. So this table shows that 2 is getting a buy in that week. Okay, second week is a black week. I again take a matching, which is 3, 4, and 0, 2. Okay, and 1 is taking rest in that week. So you have next matching we can do is week 3. So in week 3, 0 is playing with 1. So we are, this is a green. I make this matching with the green color. 0 is playing with 1. 2 is playing with 4. Okay, and 0 is playing with 1, and this time the matching is this subgraph, which consists of 2 edges, 0, 1, and 2, 4. Okay, 1, 2 is 3 is getting rest in this week. Fourth week is the blue, is the 3, 2 red week. 3, 2, and 1, 4 are playing. 3, 4, 1, 2 is playing, and 0 is getting rest in this week. And in the last week, which is the yellow week, yellow. Okay. I write yellow with green. So in the yellow, we have 1, 2, the matching is 1, 2, and the other matching is 0, 3. Okay. So in this week, 4 is getting a mark. So this graph, this color graph, Acha, can you tell me, is this a graph coloring? Is this coloring is a graph coloring that any two adjacent edges have different colors?
Yes, I think so.
Yes. And is it the what? And can you tell me what is the chromatic number of this graph?
4.
4. Yes, you're
5.
right. Not
Oh,
5.
yeah, 4. Yeah, 4.
We need at least 4 because if we take 3 colors, so we have not get the graph coloring. So at least you need 4 colors to. You can take 5 colors as well, but at least 4 colors is needed. One thing is very important for the complete graphs is that the number of degree of each vertex is same. The number of degree, the degree, sorry, the degree of each vertex is same. And okay, and that number is क्या होगा आपके ख्याल में?
4.
5 के लिए 4, n के लिए you have n minus 1. So this also means that in terms of scheduling that every team must have to play n minus 1 matches. If there are 5 teams, so they must every team play 4 matches. Okay, I'm going back to the 4 teams case, which is simpler than the 5 team case. But in the 4 team case, we get the perfect matching. We have 3 perfect matching, so we can have 3 rounds. Okay, so for example, in the first round, 0 is playing with 3 and 1 is playing with 2. This is one of the matchings I take. Okay, I call this matching the blue matching. No team left. No team has to wait for the next week. Next,
Sir,
I can, yes.
how did you figure out the number of rounds?
Yes, because we have 4 teams, and in how many ways I can take the pairs.
Oh, okay. Yeah, okay.
The number of rounds is also telling us the number of matchings, different matchings. Okay, so 1 2 3 0. The second is 1 3 2 0, and the third is 2 3 1 0. Matchings also tell us about the bijective functions. No, not bijective functions. I'm wrong. No bijective functions. Because in bijective function, you need to assign every element a different element. So the function is 1 1 and on 2 as well. Okay, so this 4 teams and 5 teams are okay. Are you okay with it? 4 and 5.
Yes, sir.
Any question? Okay, next we have 6 teams. Okay, when you take a 6 team and you are taking the complete graph case 6, this is case 6. Okay, now there is a little problem. How is the little problem? We have 15 matches because we have 6, so 6 into 5 divided by 2, which is 15. 3 games per week because we have to take the matchings. Like for example, if you take a matching 0 1 2 5 3 4, this is one of the matching because it takes all the edges. I take it with blue. Let's suppose 0, 1, 2, 5, and 4, 5. Okay, so I do this batching and then the other end. So which means that you have 3 games per week, and since there are 15 matches, so we need 5 weeks to complete the tournament. Okay, so first I take a matching 0, 1, 2, 5, and 4, 6, which is a week 1 matches. 0 is playing against 1, 2 is playing against 5, 3 is playing against 4. Now in week 2, let's move it with the red. 1 is with 2, 0 is with 3, and then 4 with 5. Okay, 1, 2, 0, 3, and 4, 5. So these are the second week matches. Next, third week, let's take green. 2, 3. Now this time I'll do like this. 2 is with 3, 1 is with 4, 0 with 5. Take the parallel ones, okay? 2, 3, 1, 4, 0, 5. Now, what about week 4? How can you give week 4 and week 5? Can anybody tell me? Let me take black. No, black is the first one. What is the problem with the week 4 and week 5? If you see the graph, you will get 2 triangles. One is this triangle I'm making with the black 0, 4, 0, 2, 4. If you see this, and one more. Let's see. Okay, if somebody is who's in the chat, that 2, 4, 3, 5, 1, 6. 2, 4, 3, 5, 1, 6. So 2, 4, 3, 5, 3 is with 5, and 1 and 6. Just a minute, I'll read 0, 1, 2, 3, 4. So there is no 6, by the way. 2, 4, 3, 5. So when you're going to 1, so you only left with a choice of 0, but they already met. They already met with each other. Okay, you are saying just replace. I take 1, 3, 2, 4, 0, 5. But 0, 5 is already played. This is the problem that you will get. Now from week 4 and week 5, so if you try to get any matching, one of the element of that matching must be in the previous weeks. Do you understand? You have this triangle 0 to 4, and so we have left with these vertices 0 to 2, 4, 4, 0, and 1, 5, 5, 3, 3, 1. So we have these 6 edges, and these 6 edges makes 2 triangles, 2 disjoint triangles. One triangle is this one, I made it with black 0 to 4, and the other triangle is 1, 3, 5. So what is the problem with that? So the problem with that is that you cannot get you always get a vertex twice. You're not getting so when let's say if Hassan is saying that you take 1 3 and then 2 4, so 0 5 will be the match which is already has played in week 3. So can anybody of you give any solution? Or you can think maybe a wrong solution, but please think now what to do, how to get rid of this thing. We are stuck.
Should we change our matchings in the previous weeks?
Okay, but can can you can you have any generalized way in which you will do any type of things, you will get the schedule of the tournament. So this thing which we are seeing, that if we take this type of, you're right, all right, but this type of, when I take this type of matching, I'll stuck. So I must have some solution then in which I do some different things, but every time I'll get a proper schedule in which there is no repetition of matches. So think a little and tell me what can be possible. Okay, I'll give you a solution to this problem. So how to solve this problem? So first, do label the teams through 1 through n, not 0 to n minus 1, but do 1 to n, and uh, put 1 in the center. Like it's like we have an example of a 6 team, so 1 2 3 4 5 6. So we have if we take out you can take vertices of the pentagon and take the center point as 1 and name the other vertices in the clockwise. So 2, this is 2, this is 3, this is 4 5 and 6. Okay, we are considering the even number of cases. ये जो problem जो मैं solution बता रहा हूँ, this is for even number of teams. So we have 6 teams. We now name from 1 to 6 or 1 to n, and we put the first element 1, first team 1 in the center and the other in a clockwise direction. Now I do the make a table. Okay, a table is 1 2 3 and then in the reverse order 4 5 6. Okay, so make a table like this in which you place each number from 1 to 6. In the first row you will go in the increasing order 1 2 3, and then below the 3 you will write 4 and go in the left direction and writing the other vertices 4 5 6 like this. Okay, and then in 1 week you will take the matches which are in one column like this. They are in one column, so 1 is as a played against 6, 2 is played with 5, 3 played with 4, and you connect these numbers. So 1 is played with 6, you connect with 1 with 6, 2 is playing with 5, you connect 2 with 5, and 3 connect with 6. So sorry, 3 connect with 4, this is 4. Okay, and you can now what will be in the second week? Because in the second week just move you fix 1 the center position and move all other to one place to the next place clockwise. So you put 6 in place of 2, place 2 in place of 3, place 3 in place of 4, and place 5 in place of 6, and so on. Okay, so when you do this, so actually you are doing this thing, that in this table So you the one position is the fixed position, and you change the other position. So 2 is goes in the position of 3, 3 goes in the position of 4, 4 goes at the position of 5, 5 goes at the position of 6, and 6 go at the position of 2. So the graph, what the graph you will get. So 1 is in the same place. You shift 6 here at the position of 2, 2 at the position of 3. Now 1 is playing with 5, 4 with 6, 2 with 3. So this is the next week. And the third week, again, you will do the same thing with this thing, that you fix one and change the positions of the other. So in the other week, 6 comes at the position of 2, 2 comes at the position of 3, and so on. So, and do these things till you get the first table again. So this is a general way of scheduling the Robin when you have even number of teams. Okay, when you have even number of teams, so you can do this. And in any way you can start from any because if you do not start from this table, you can start from this table and do the same thing. You will get all the possible matches, and you do not get any mixing, and not any, there is no repetition in a week of matches in some week. Okay, do you understand this method? If you understand this question, then I'm going to ask a question from you. So first tell me, do you understand this question, this solution?
Sir, I had one question about
Yes,
this.
yes.
Sir, like we were talking about the possibilities of like the 6 teams playing against each other, right? Two, like this. So one possible, like except for this method, one possible way was also like making combinations, right? Like if we take A B C D E F, so we can do A B C D E F and then A C and then B E and then F and D, like this, making combinations to figure out which team plays which team in that game.
Yes, you are right. We were doing this thing here in 6 teams. We are doing the same thing, but for example, this in this particular configuration which I'm taking, that in the first week I take 0 1 2 5, 2 is playing against 5, 3 is playing with 4, and in week 2 I'll do this thing, and in week 3 then I stuck in 4 and 5 thing. You are right. This is a one way of doing this thing, but this is not a general way. For example, if somebody started with these 3 weeks, these 3 type of matches in these 3 weeks, you will get in fourth and fifth week that you do not have any, you cannot complete your matches in 5 weeks. You need some repetition, like if you take 1 3 and 2 4. So this method is good, but for some configurations, like I take in this example, we will be stuck. So we need some other method, other elegant method in which we take any configuration. Like for example, I say this method. In this method, I take any configuration, any pair of numbers like 1 2 3 6 4 5, and then what I do, just I need to do like this, that I graph like this, that I fix one of the team, like I fix one and put all the others in the clockwise ways, and just turn this clockwise, just change the positions by one, and fixing the central one. In this way, I'll get the all the matches, and any configuration I'll take, this will work. Okay, so do you understand my point?
Yes.
This method is okay, but there is some problem in some of the configurations. Okay,
Yes, sir.
so
Understood.
okay, good. So now the question is, this case is for even numbers. Okay, ये जो अभी हम कर रहे हैं, even numbers. What do you think, is this the same thing valid for the odd numbers? And if not, how can you fix that problem? So for example, if we have 5 teams, what about for 5 teams? Anybody? What the
Should we fix more than one number?
fix more than one number? Then what happens? Let's suppose we have teams 1, 2, 3, 4, and 5.
Sir, I think we can do the playing and the sitting thing. Like 4 teams could play, and then one team like could not play, and then using these we can.
Yes, but I want this method. So can this method is used, this method for the odd number, or maybe with some modifications it can be used? You know that whenever we have odd number of teams in one week, one team must get a bye, whether they are 7 teams, whether they are 9 teams, one team is get a bye. Okay, so let's do like this, that we add a number 0, which means now how many these numbers are? These are even numbers, even number of teams. So whoever is playing with 0, it means that that team is getting a bye. So for the even number of teams, we have solution of this thing: 0, 1, 2, 3, 4, 5, and so this table tells you that 1 plays with 4, 2 plays with 5, and 0 gets by. Okay, so this means that we can work with the same method for the odd numbers of teams. Just add a number 0, and the number 0 is paired with which number that team or that player will take a bye. Okay, so understand how this method be used for odd numbers.
Yes, sir.
Yes.
Okay, a little generalization or extension of this method. So usually you have seen in the league games that the scheduling of the games involve home and away games as well. That the team plays a home game as well as away games. So for this we need a graph, which is directed graph. So this is a directed graph, and these arrows shows the for example, in this edge 1 to 0. So this means that this match is played between 1 and 0. One is playing away and 0 is playing at home. So the arrow pointed towards the team which is playing in the home. Okay, so let's suppose 0-2. If this is 0-2, so 0-2 means that 0 is playing with 2, but 0 is playing away and 2 is playing at home. Okay, so what about such things, that how do we cater home and away games? How do we cater that every team gets the same number of home and same number of away games? Or if it is not possible that everybody gets the same number of home and away games, then there must be some the symmetry in the home and away games, that there should be not like this, that for example in this figure, if this is a figure is the schedule of some tournament between 4 teams, so 0 is playing 2 away matches and 1 sorry, just to make a So away and home. So 0 is playing 2 away and 1 home. And if you see 2, 2 is, sorry, if you see 1, so 1 is playing 2 home and 1 away. And if you see 2, so 2 is playing 2 home and 1 away. And if you see 3, so 3 is playing 1, so 2 away and 1 home. Okay, so how will you get the, if you see these numbers are in degrees and out degrees of the graph, as we have mentioned. So in degree of a tournament would refer to a number of home games a team, and the out degree of a tournament would refer to the number of away games a team would play. Okay. So again, let's see some situations. We have 4 teams. So in the round 1, if you see 0 is going away, plays with 2, which is playing at home. Okay, I'm writing A with for home, or A away, and H for home. Okay, next for black, uh, the next round 3 is playing with 2, 3 is going away, and 2 is at home. Okay, in the first round, the second one is 3 and also is playing with 1. So 3 is going away. Okay, 3 is going away and playing with 1, which is playing at home. In the second match will be 1, 1 is going away and playing with 0, which is at home. And the last one is blue. 0 is playing with 3, 0 is away, and 3 is at home, and 2 is playing with 1. Okay, so team 0 is playing 2 away, 1 home. So I'm writing here 2 away, 1 home. Team 1 is playing 2 home, 1 away. Team 2 is playing uh, 2 home and 1 away. And team 3 is playing 2 away and 1 home. So there are 2 teams which are playing 2 homes, and there are 2 teams which are playing 1 home. And the vice, and 2 are playing 1 away, and 2 are playing 2 away. So how to schedule where the number of home and away games different in absolute value 1? Like in this figure, if you see this figure, this is a better solution of in which the home and away games differ in absolute value 1. So in the round 1, as you see, let's call the round 1 the red one. 0 is playing 0 away, playing with 2 at home. So round 1 में दूसरा मैच है, we have 3 playing away with 1 at home. In the round 2, just black, 3 is going away to play. Okay, the important thing, sorry, I missed one thing, I'm going back, is that team 0 is playing so team 0 is playing first match is away, then second match is home, and the last match is away. I missed this thing, right? 1 0 is playing with 3. Oh yeah, 1 is 2 is playing with 1. So team 0 is play away, home, away. team 1 is playing home, home, and then, sorry, team 1 is playing home, away, home. And team 2 is playing home, uh, and then home, and then away. Okay, and team 3 is playing, uh, away, then away, and then home. So most of the time it is desirable that the teams play alternate games, one away, one home, one away. And in some of the time, it is also desirable that they play a few matches, a few string of matches home, and then few string of the matches away. So, uh, so what is a good solution, or is there any solution of getting the So one way of scheduling the tournament is do the scheduling in two ways. Okay. In one way, in phase one, you will do the opponent scheduling, that you schedule all n/2 matches for each of n-1 rounds. So, and in the phase two, you will assign the home and away matches to each team. Okay. So I'm just finishing my thing on these things, that two consecutive home or away games is called a break. This term is called, if you have two consecutive home or away games, this is called a break. And this is a result which said that any home away assignment for an opponent's schedule cannot be done with fewer than n-2 breaks. This is a very important mathematical analysis, that you cannot do any home away assignment for an opponent schedule, the phase one, with fewer than n-2 breaks. आपको at least n-2 breaks करनी पड़ेंगी. ठीक है, जैसे फॉर एग्जांपल यहाँ पर अगर हम देखेंगे, ये दिस इज द सेम एग्जांपल, दिस वन, that in assigning like this, you have, here is a break and here is a break. Okay, break means that you have a consecutive home or away matches. So we have here team 2 is playing two consecutive home matches and team 3 is playing two consecutive home matches. So you have two breaks. So the theorem is that you have you cannot have fewer than n-2. So here it is 4. So 4 minus 2 is 2. So we have in this case exactly two breaks. So we do not have less than two breaks. So this is the theorem which can be proven. So do you understand this result? Any home away assignment for an opponent's schedule cannot be done with fewer than n-2 breaks. And we can prove this thing. And the idea is that no two teams can have identical home away patterns. By the way, all these things are for the even number of teams, because when we have even number of teams, they are playing odd number of matches. Let's suppose we have 8 teams, then they played 7 matches. We have 4 teams, they are playing 3 matches. So whenever we have 3 matches or 7 matches or odd number of matches, never it happens that they can play equal number of home and away matches. But if there are odd number of teams, then it is possible that they can play, because when there are odd number of teams, then each team have to play even number of matches, and when they have to play even number of matches, so half of them can be away and half of them can be home. So for odd number of teams, there is a solution, but for even number of teams, there is no solution, except that we can do as few possible breaks as it possible. And how many fewer possibles breaks can be possible? They are n-2 breaks. And why this is true? The idea is that no two teams can have identical home away patterns. किसी का भी जो home away का pattern है वो identical नहीं होगा, because if it happens, then there is some pair of team which cannot then it happens that no two teams play with each other, because in the Robin round system we have this, that every team must play uh, to each team of the tournament of the league or of the tournament. Okay, so if it happens that two teams have identical home away patterns, then it is possible that there is some team which do not play with some other team. Okay, so this is the idea. So can you from this idea, can you tell me how this is possible that these are n-2 breaks? So for example, if you see this example of of 4 games, so every possible pattern is there. Away, home, away, home, away, home, 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 away, 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 home. Okay, so if there is no identical pattern, so there is at most one, there is at most, I don't know. Yes, it's working. So there is at most one team which starts to play at home and play alternatively, and ends at home. Like in this example, if you see, team 1 is starting with home and then away and then home. Similarly, there is one team which started at, there is at most one team. Similarly, there is at most one team which starts to play away and play alternatively, and ends at again away. So these are the only two possibilities in which the one team at most one team plays like this in this pattern, and one team plays in this pattern, and all other patterns in the all other teams will have be a break, will take a break. So which means that you must have to do n-2 breaks. Okay, so the solution of this is sometimes is that the tournament is played round robin, but in this is not a single round robin, but it is double round robin. That in the second stage, in the first stage, all played with each other. Some are home, some are aways, and then in the next round, the the team which play, let's here like zero played away with the two, and two played at home, then it goes like the reverse, that two will played away with zero at home. Okay, so in this way the things are equalizes. So in most of the leagues, like you see IPL, if you follow IPL, so in IPL there are 8 teams and they play with each other twice, and every team play with the other team one away match and one home match. So this is one of the solution of this home and away thing. So there are many other, I have mentioned bipartite and tripartite as well. They are also used in some other type of tournament scheduling. Okay, if you have any questions, please ask me. This is the end. Any question, any remark, anything? In the last, I do very fastly, but this is because of the less time. You can watch the recording as well. So no question. Okay, if you have no questions, so see you on Friday. Allah Hafiz.